I don't know if we'll get to those, if we'll get to that set of notes today, but if not, then that'll be what we talk about on Monday. So here's where we're at in our electrophilic aromatic substitution chapter. And where we were at was, now we're talking about doing electrophilic aromatic substitution, adding an E plus to a ring that already has a substituent on it. Bless you. So the role of that group is that it either causes the reaction to occur faster or slower, which is an activating or a deactivating group, and then it will also tell the electrophile where to go. So we have both of these, and we have to explain or at least lay out why does a group activate, why does a group deactivate, but more importantly, how does a group donate electron density, how does a group withdraw electron density from the ring. And so here are our groups that are activating by just experiment and that are deactivating. So basically the hydrogen here, this benzene is our baseline. So if you have an N or an oxygen group attached to the ring, it goes faster. If you have a ring, it goes faster. And if you have an alkyl group, it goes slightly faster than benzene. If you attach a halogen, carbonyl, C triple bond N, which is a nitrile group, a nitro group, or an NR3 plus, an ammonium group. Those all go slower. And the way these are ranked in terms of number 1 to number 10 is they're ranked according to their speed. So halogens go faster than carbonyls. And carbonyls go faster than C triple bond N. That'll become important towards the end here, bless you, because the next question is going to be, what if I got 2 groups on the ring? Or 3? Who's going to do the direction? And the simple answer is whatever group on this list from 1 to 10 is the highest. But that's sort of where we'll hopefully get towards the end here. So now the question is, how do the activating and deactivating groups increase or decrease the rate? And again, if we're talking about an electrophile, we're talking about the nucleophile ability of the ring or the nucleophilic ring. Then what we have to talk about is how do we push electron density in to make it go faster? How do we pull electron density out to make the ring less electron rich so that the reaction goes slower? And that's kind of what we talked about at the end of class on Wednesday. So there's 2 ways to do this. 2 ways to push and pull electron density. One is called inductive. So inductive effects are you're pushing or pulling electron density in or out of the ring using a sigma bond. Well, what does that look like? That's as simple as saying, okay, I have a halogen attached to my ring. That halogen atom is more electronegative than the carbon, so it's pulling electron density away from the carbon, and therefore it's pulling electron density out of the ring. So this would be an electron withdrawing group. How do you push electron density into the ring using basically electronegativity and a sigma bond? Well, I could ask you this, but we'll just cut right to the chase. What happens when I attach an alkyl group to the ring? As we've done how many times this year, the hydrogens are delta positive in an alkyl group. The carbon is delta minus. That delta minus carbon can now push electron density into the ring, just like it did a double bond, just like it did a carbocation, just like it did a radical. So both of these are examples of inductive effects. The alkyl group, electron donating, so this would be an electron donating group. The halogen, electron withdrawing. So we're using a difference in electronegativity when we do induction. And these are two of the examples for induction. Right, does that make sense to everybody? I'll add one thing to this, and that is induction is kind of weak compared to resonance. Resonance is a much more powerful way of pushing or pulling electron density. But then that asks the question, so what is resonance? So when I do resonance donation or resonance withdrawal, I'm going to push or pull electron density by forming different resonance structures. And I'll show you the examples of how we do that. Okay. So these are our two effects. And at some point I'm going to go back to that table of 10 groups, and we're going to label which ones do this by induction, which ones do this by resonance, which groups do this by both. And at some point next week, we'll have a quiz at the beginning of class where you have to write the groups from number 1 to number 10. You've got to tell me whether it's induction or resonance, and you have to tell me whether it's an activating or deactivating group. Because you got to learn that. Because that's what we need for to be able to do these reactions. So here would be an example of resonance. I take a group that has a lone pair of electrons, and that atom that has the lone pair, the X group here, that is attached to the ring. Now this could be an oxygen group, or it could be a nitrogen group. Nitrogen being number 1, oxygen being number 2 on the list. I'm going to combine those two together and say, I've got this atom that has a lone pair. It's probably unfortunate that I used X because you're going to think that's a halogen, although that might not be that bad. That might not be that unfortunate in a few minutes. So when an atom has a lone pair and it's attached to a ring, what it can do is donate the pair of electrons, as it shows with this arrow, and then that pair of electrons goes to the carbon so that we basically form a positive charge on the atom, oxygen or nitrogen, and then the ring gets a negative charge. And then we can draw a second resonance structure and a third resonance structure with that negative charge. So that lone pair that atom had is now basically able to be donated to the ring through forming these different resonance structures. And these should all be delta minuses because the minuses got separated from the delta. There's no way I can fix that. Okay. So in the resonance hybrid, you can see the ring has picked up a delta minus charge. From where? From the donation of that lone pair. So this is a resonance donation of electron density. Okay. So that means that nitrogen and oxygen groups push electron density into the ring. They are activating, they are donating groups, and they donate by resonance. You might say, but if I add a nitrogen group to the ring, won't the nitrogen pull some electron density out because it's more electronegative? Maybe. But that's an inductive effect. And anyway, what I know is, I know that when I put a nitrogen or an oxygen group on the ring, it reacts much faster than benzene. My best example of that is back in the day, like, I don't know, 20 some years ago, when I first started and we had a master's program, which we did at one point, one of the graduate TAs was trying to add iodine to the ring. They had a sort of an environmentally friendly way of adding iodine to a ring. We haven't talked about adding iodine to a ring because it's not easy. So she just asked me in lab one day, she said, what would be the reaction that would occur the fastest? And I pulled out the chart and said, well, it'd be a nitrogen group attached to the ring. So she got a nitrogen with a C double bond O CH3. That's what we're using in lab, right? We just destroyed that this week. We just took that and C double bond O CH3, we just took the amide off and made it an amine. So it was really easy to find. So she went to do that reaction, and then I think the next time I saw her, I said, so did that work? And she goes, yeah, it basically was so reactive that it just sprayed stuff all over the hood. And it took me like an hour and a half to clean up. Okay, it was the most reactive. She just asked what would be the most reactive. She didn't ask about whether or not it would explode all over the hood. But that's how reactive that was. So these two groups are the most reactive because they can donate electron density by resonance. And would you have to do something like this? Maybe. If you look at some of the older exams, I might ask to write out all the resonance structures. But I'm going to come back to those. Because we're going to have to talk about these resonance structures when we talk about where does the group add. Right now, all I'm doing is showing you that the group can push electron density in. All right, let's go down the list. So nitrogen number 1, oxygen number 2. Number 3 is a phenyl ring. Carolyn?
Why is the positive not a delta positive on the hybrid?
Because in all 3 of the resonance structures, there's a positive charge.
So you don't have to take into account that first structure?
I mean, we could. That probably would be a delta positive if we took them all into account. But of what I'm really showing you is by forming these 3 resonance structures, basically I've taken and I've put a -1 charge into the ring. So yeah, it could be looked at as a delta positive. But the key thing is the rest of the groups are all negative. The ring itself is negative. So then if we have a ring, which is number 3, we can still do resonance. So you can see I've just written all of these resonance structures. And you might say, are these really, really realistic? Because why would one ring become slightly positive at the expense of the other ring becoming slightly negative if they're symmetrical? And I would agree with that question. Like, why would it do that? So basically we're in a position where we experimentally know that when you attach another ring to a ring, it makes one of the rings go faster. And this is how we explain it. So we'll just leave it at that. So one ring is going to become slightly positive at the expense of the other one becoming slightly negative, so therefore one of the rings is activated. It's not a very big effect. It's less than oxygen and nitrogen because this group is number 3. Then we go to our alkyl groups. Wait, where are our alkyl groups? That's a good question. Where is my alkyl group? Oh, here's my alkyl group. It's one slide ahead. So alkyl groups we said we're activating, and that's because when you have a carbon group attached to the ring, the hydrogens become slightly positive, and that leaves the carbon slightly negative to push electron density into the ring. So that's the inductive effect. And because alkyl benzenes on our chart, the alkyl benzenes are number 4. They're right above benzene itself. that means it's a weaker effect. Because they're just barely more reactive than a benzene ring. Okay. So now let's go back. We'll do benzene in a minute. I've kind of shown you the halogens. Halogens, when they're attached to the ring, will pull electron density out by induction as well. But what about carbonyl groups? Actually, what about any group with a multiple bond? So this would cover a carbonyl group attached to the ring, which is number 7. This would be a C triple bond N. And this would also be an N double bond O, O minus with the positive charge of the nitro group. So this is number 7, 8, and 9 on the list. Okay. They all have this general formula of X double bonded to Y, where the X atom is slightly positive in the polar covalent bond, and the other atom is slightly negative. So that's true for a C double bond O, a C double bond N, or an N double bond O. So all of these have the atom attached to the ring is slightly positive, and the other atoms is slightly negative in their polar covalent bonds. So how does this now withdraw electron density from the ring? Here are the 3 resonance structures you could draw. And so I'm going to start by taking this pair of electrons, moving it to form a double bond, and then moving that pair of electrons in the X multiple bond Y to the atom that has the slightly negative charge in the polar covalent bond, so the electrons are moving in the right direction. And when I do that, I get 3 resonance structures. Again, now that means I've sucked electron density out of the ring. It is now electron poorer, which means it's going to react slower. Okay. So that takes care of number 7, number 8, and number 9. Just by using this general structure of X double bond Y. Right. Is everybody kind of with me? I get daily emails that say I'm not supposed to ask that question because it really doesn't tell me anything. I'm supposed to ask you a more specific question so you could demonstrate that you're with me, but it's Friday. Okay. So that's how we can justify where these groups show up on the list that we get by doing the experiment, which was number 1 to number 10. That leaves us with the halogens and the N plus as the final 2 groups that we should probably try and justify. So alkyl groups, we've already seen that's an inductive effect. The halogens are an inductive effect. And when I go back to the chart, and you have it in front of you right now, around the benzene, one up is inductive, and one down is inductive. So that just shows you that the inductive effects, being just a little bit more reactive than benzene or a little bit less reactive than benzene, those 2 groups tell you that the inductive effect is really weak. Because everything else that's resonance is either much more reactive or much less reactive. So halogens then withdraw electron density through the sigma bond, and that's induction. The N plus has a number of issues. You could say, yes, it is an inductive effect, but there's a bigger effect. And that is that if I take a benzene ring and I have four groups attached to it, so it's a positive charge. And then I try and react an E plus with it. I'm trying to react to two positively charged species together. That's not going to happen very easily. As a matter of fact, some textbooks just say that this reaction, that's a no reaction. Because I'm trying to react to two positive reactants. That's just not going to happen. So it's really not so much an inductive effect. You might say, but wait, you just said that inductive effects were weak, but yet the most powerful electron withdrawing group is an inductive effect. It's not really. It's the fact that you're trying to react a positive with a positive. Okay, so that's sort of how we can push and pull electron density using resonance and using induction. And that's how we justify number 1 all the way down to number 10 on the chart. Right. Kind of makes sense? So then here's my new chart. Everything above benzene is going to be called activating. The first 3 activate by resonance, the 4th one by induction. These number 7 through 9 deactivate by resonance. Halogens deactivate by induction. And then really the N plus just doesn't want to react with anything that's positively charged. And so this is kind of the chart you're going to need to know for next week. Number 1 through number 10 in order. What's the activating, what's deactivating, and how they activate and deactivate by induction, resonance, or potentially both. I didn't show here that a halogen or that a carbonyl group or an X double bond Y has a slightly positive and a slightly negative charge. You could argue that this carbon is pulling electron density out of the ring because it's slightly positive. So that's an inductive effect. And I would argue that, yeah, that's true, so maybe you could label these as both. But resonance is more powerful. Jacob?
Is the resonance effect, like, does it add on top of each other? If you have 2 nitrogens attached at different points to the ring, would it
Yes.
pull and not?
Well, so if you add different groups, you're going to activate or deactivate the ring independently. So if you had 2 nitrogen groups on the ring, that's going to be more reactive than just having 1.
Okay.
If you had a nitrogen group on the ring and maybe a carbonyl, they might begin to cancel each other out. We're not necessarily going to talk about the kinetics of that, but we are going to talk about where the groups go when you have an activating group on the ring and when you have a deactivating group. Because what's going to happen is activating groups are going to direct to one position, deactivating groups are going to direct to another position, and then the question is which one's more powerful. So we'll get to that, but we won't really talk about it in terms of kinetics, but if you wanted to, 2 activating groups would cause it to react faster. I don't know if it's a linear effect or not because there aren't any linear effects. They're all logarithmic because they all are activation energy in that. Okay, so that's our activating and deactivating groups. Now, regioselectivity. Right? We talked about regioselectivity for a while. I don't even know if we talked about it this semester. But remember regioselectivity when we talked about adding something to the double bond. For Regios, like if we added HCl to a double bond, maybe with 2 R groups here and 2 H's, if we added HCl to that double bond, the reaction would have been regioselective, because if I add the H to one carbon and Cl to the other and then go vice versa, I get 2 different products that are structural isomers of each other, meaning they have different names, and I selected one over the other, which was a selective part. So these reactions are going to be regioselective. So if I already have a group on the ring, and I want to add my electrophile, whatever way possible, that electrophile's got to go somewhere. Does it go ortho to the group that's already on the ring? Does it go meta? Does it go para? And I mean, if this was just a random set of reactions, we'd move on. We'd just say, oh, it's random. There's no way we can understand it. Let's move on. Well, there's notes that follow this that we're not moving on. So there is a system here. And there usually is a system, right? And a system usually is, if you do one thing, you get one set. If you do another thing, you get another set. So that's also going to be the case here. So we do this reaction. People did this reaction. What they found was that if you had an activating group on the ring, the electrophile would add to both the ortho and the para positions. Those were the major products of the reaction. The major products of the reaction would be ortho and para. And I guess another way I could say that is that you don't get any meta product. And at some point, we're going to probably argue that the ortho product might have some steric issues here with the activating group. So maybe you'll get more para than ortho. But right now, we're just going to say you get both ortho and para products. You don't get any meta. Okay. So that's if you have an activating group on the ring. And this is why we need to know what our activating and our deactivating groups are, because we're going to want to write the major product of the reaction. Then what you find is if it's a deactivating group, you end up with only or majority meta product. And so what the deactivating groups are called then is meta directors. That means this deactivating group directs the electrophile to the meta position. The activating groups are called ortho-para directors. They direct the E+ to the ortho and para positions. And so that's why we need to know those groups. And that's the way it breaks down. So if you do this experimentally, this is what you find. Except there's one exception. And the exception is that when you react halogenated benzenes, you get ortho and para. But halogens are deactivating. So how does that happen? Well, we'll get to that in a minute. So this is the exception to the rule. Halogens are deactivating, but they're ortho-para directors. So there's another column that's going to be on your quiz next week, and that is what kind of direction that they give. This is usually one of my easier graded quizzes, because hopefully everybody gets it right after you go through and memorize this table, or memorize the results. Memorize, bad word, learn. So why? Why do activating groups give ortho-para? Or in other words, why is meta bad? Why is it not formed? And then why is meta It's favored. So then here's what we have to do. And there's been times when I've gone to the board and written all of the possibilities out and had you dutifully write it down as I did. But we'll just go ahead and put this on the chart, and then hopefully, if you're still awake, you can kind of see the patterns here. Here's my X group, my oxygen, nitrogen with a lone pair. Oh wait, what also has a lone pair? 3 lone pairs. What group has 3 lone pairs when it's attached to the benzene ring? Halogen. So well, cat's out of the bag. Why do halogens, why are they the exceptions? Because they look like oxygen and nitrogen because they have lone pairs. Even though they're deactivating, they fit this general formula. So everything I'm going to do here for an oxygen and nitrogen, I can do for halogen, and that's why the halogen is an orthopara director. But here's what we have to do. We have to basically add the electrophile to the ortho position, write all the resonance structures, then add it to the meta position, write all the resonance structures, add it to the para position, write all the resonance structures, and this reaction is going to go to give the major product that is the one that has the most stable resonance structures. So we do that. So we add electrophile to the ortho position and put the plus charge up here next to the oxygen, nitrogen, or halogen group, and then we can write all of our resonance structures. So we get 3. But when the positive charge is next to the atom with the lone pair, the oxygen or the nitrogen, I can get a 4th resonance structure. And again, let the cat out of the bag here. Whenever the plus charge is next to the substituent group, something's going to happen. Either that's going to be more stable or it's going to be less stable. And in this case, that resonance structure, then, the resonance hybrid, is going to be more stable because it's got 4 resonance structures. Because I can take this positive charge and donate the pair of electrons from the oxygen or to nitrogen or to halogen. So now I've got 4 resonance structures. Let's go to meta. I add my electrophile to my meta position. That puts the positive charge here, and here, and here. And where did the positive charge never go? Next to the substituent. And so that's it. I just have those 3. I can't form a 4th resonance structure because the positive charge never went on that carbon. All right, so when I added ortho, I had 4 resonance structures. When I add meta, I have 3. Guess what's going to happen with para? I'm going to get the positive charge in 3 places, one of which is going to be next to the substituent, and voila, a 4th resonance structure. And ortho always basically has the same characteristics as para or vice versa. So, just to recap, what happened? When I added the electrophile ortho, I got 4 resonance structures. When I added meta, I got 3. When I added ortho, I got 4 again. So which intermediates are the most stable? The ones with the more resonance structures, the ortho and the para. Because any group with a lone pair on it, oxygen, nitrogen, or halogen, can form that 4th resonance structure. So this is how we justify why the activating groups of oxygen, nitrogen, and the exception of halogens all give orthopara products with very few meta. So then we just keep doing this. We do it with the ring. Actually, we do it with the methyl group first. There's no ring. You can imagine what would happen if a ring was on there. Right? When you put a plus charge next to the ring, what happens? You can then write your resonance structures inside those other inside the ring it's attached to. What about an alkyl group? Well, in an alkyl group's case, there's no fourth resonance structure. And we can fit it all on one slide. So we can add it to ortho. We end up with 3. We end up with 3 if we do meta. We end up with 3 if we do para. Oh no, what I just told you must have been a Y then. Because I said it would always, the plus charge when it was next to the group, that was the special position. It still is. If we look at the types of carbocations we have, when the plus charge is next to an alkyl group, it's a tertiary allylic carbocation. When it's not, it's secondary. So notice that when I add the electrophile, ortho, and para, what do I get? I get 2 secondaries and 1 tertiary. When I add meta, plus charge is never next to the alkyl group. So it's 3 secondaries. So adding ortho and para, I get the additional more stable tertiary, and so then that gives me more stable intermediate for ortho and para. So there's the activating groups. Maybe I should assign doing the phenyl as a take-home quiz. I'll think about that. What about deactivating? Well, the first thing when you look at the deactivating is you see the big red hash mark through one of the structures. So I'm going to do the same thing. Only now let's do it with an X double bond Y. Remember, X double bond Y is carbonyl, C triple bond N, NO2. So now what I do is, now I add the electrophile to the ortho position. I get these 3 resonance structures, but notice there's this big red thing through the structure where the positive is now next to the X double bond Y group. And then you might say, well, why? Why is that? Well, when the positive charge is sitting next to an X double bond Y group, remember the X double bond Y group, the X atom was slightly positive and the Y atom was slightly negative. So if this was a carbonyl group, the carbon would be slightly positive, the oxygen slightly negative because it's a polar covalent bond. So when you put a positive charge next to a delta positive charge, that's bad. Well, not to pass judgment, it's not favorably energetic. So now with an electron withdrawing group, you can kind of imagine what happens. When it was electron donating, putting the positive charge next to the substituent was good because I got an extra resonance structure, an extra stable resonance structure, which made my ortho and para favored. But now when I put the positive charge next to the substituent, which group is going to be favored? Adding it meta, because then there's never a positive charge next to the deactivating group. So in this case, the reason I did put this through is, as it says, this resonance structure does not form. It may form, it's just really, really unstable. So I'm going to say 2 resonance structures for ortho. 3 for meta, since the positive charge never was next to the substituent. And if I go back to para, again, the positive charge goes next to the X double bond Y group, which is unstable. And so in this case, 2 for ortho, 2 for para, and 3 resonance structures for meta. So what's favored? The meta product. So this is how we rationalize the idea that an activating group directs ortho and para And a deactivating group, with the exception of halogens, directs meta. And the halogen group directs orthopara because it's got a lone pair and it looks like the oxygen and the nitrogen. So that's how we rationalize all of this. Does that make sense? Is there anything that doesn't make sense out of that? So this is a lot of stuff. There's a lot in these slides that we're just going to go ahead and summarize. So with the halogen, we've already done that. The halogen has lone pairs. So then we're back to this chart. And then there's an even bigger chart if you'd like to use that. And there's probably a chart in your book. Well, I'm sure there is. One of the things that I do, though, is I treat all the carbonyls the same. I don't know what's more activating, an aldehyde or a ketone. I don't care. Because I'm the one that's controlling the problems. So when I give you carbonyls, I treat them all the same. Now, I didn't write the top hat problems, so they may have a slightly different order, so you might have to look at their table when you're doing those problems. And nitro groups, of course. And then some of these groups they consider strongly deactivating. They'll react. It just requires a little bit of heat. Maybe I should show you the most famous example of that. That was last time. That was last time. So let's do a problem. I know, it's been 45 minutes of non-active lecturing. So let's do a problem. I'll take toluene and I will react HNO3, H2SO4 to that. What's the product? All right, tell me how to write the product. How are you going to write the product, Kaylee? You sort of raised your hand until I looked, and then it went back down. Okay, so first thing we have to do is when you react nitric and sulfuric acids, what's the electrophile that you get? And you get an NO2 plus. And so where then is that NO2 plus going to go? Where is it going to substitute on the ring? Jacob?
Meta.
Okay, I hear a meta. David? I hear an ortho and a para. Those are the two possibilities. I'm glad you said meta. How many people say meta? That the nitro group's going to add meta? You're all by yourself. Orthopara. You're not that far all by yourself. And everybody else? I know. It's Friday and I'm doing a problem in the last 5 minutes. I've just violated 2 fundamental educational rules. I'm supposed to sum up. I kind of am. Okay. Who is the director? Who's doing the director? Michael? The methyl group is doing the directing. And that's one of the things that you can easily get confused with when you first start doing these problems. The nitro group, if you look at the nitro group, you say, oh, well, that's a deactivating group. Yes, it is a deactivating group, but in this case, it's the electrophile. So it doesn't self-direct. It's the group that's already on the ring does the direction. So the methyl group is going to direct the nitro group to the ortho and the para position to itself. The electrophile, it doesn't matter what the electrophile is because the electrophile is not the director. Okay. And that's the reason why I asked this question. I've been doing this a long time. And every day it's even longer. But the reason I ask this problem is because I can sometimes get people to say, oh, the nitro group's going to add meta because it's self-directing. No. The group on the ring is the director. Okay. So when we first start out, that's a common mistake that we make, is we forget who's directing. The methyl group is directing, so I would get ortho and para products. So now I've made a nitrotoluene molecule. And if you were somebody like, let's see, no, Alfred Nobel made nitroglycerin. That's how he built up his fame and fortune. He's like allegedly the 6th cousin of my great-grandfather. But if you have any kind of Swedish heritage, of which I have 16% according to Ancestry DNA spit test, then you would have a familial relationship with Alfred Nobel. Those tests kind of change your opinion of what your ancestry is. Just that's another class of discussion. But so what Nobel did was he made nitroglycerin. Somebody else made TNT, which is trinitrotoluene, and I'm 1/3 of the way to trinitrotoluene in this step. So on Monday, we'll ask the question, okay, I want to add another NO2 to these two molecules. How do I handle multiple groups? So we'll deal with that on Monday, but the answer is you got to know number 1 to number 10 in order. All right, there's going to be no take-home quiz. I think you do have some problems, top hat problems from chapter 20 to do. So on Monday, I'll have some more practice or take-home problems. But other than that, you have the weekend free to get caught up.
Can I turn this into you on Wednesday?
Yeah.
Thank you.
I haven't graded them yet, so and I'll put the answer key up sometime today.
Thank you.